Good morning, all of you. Today we will discuss about the shape of the data, its decoding the skewness, a statistical guide for better management decision making. So, what do you mean by skewness? Skewness mean the data is not in the proper symmetric shape. For example, there are five students in a group. Their age, let's say we take their marks. The first student, their marks is 20. Second student marks is 15. And third student marks, say, 20. And another student, 30. Another student's 90 marks, right? 90 marks. And based on this, can you tell me what is the average marks of the students? Out of these five, what is the average marks? What's the average marks of the students? How do you calculate? Sum of x divided by number of observation. Here sum equal 5 and 3, 5, 8, 8 plus 170, right? Altogether 175, and it's be divided by 5. Then what's the average?
35.
35, right? Now, so if we say the average marks of the student is 35, is it true? Is it true? Look at here. If we draw these marks in a timeline, in a line, here 15, 20, 20, 30, and 90. The central position is where? According to this, 35. This is mean. Based on this data, it's based on this calculation. If we say the average marks of the students is 35, it's right. It's not. It misleads because out of 5, 4 students marks below 35 only, right? Only because of this only one observation, one student marks, it, right? It's bringing the mean here. So we studied a term for this kind of values, this kind of extreme values. It's called what? Outlier. Outlier. Outlier, right? Outlier. So this kind of data maybe mislead our decision and inferences. So this kind of data distribution is called skewless data, skewed. Normally, asymmetric data have this mean, median, and mode should be equal. At least approximately equal. Then only we can say it's symmetric data. So when the data is skewness, if there are any outliers in data set, in a sample data set, mostly the mean value may bring us further inappropriate inferences. So therefore, we may prefer to use what? Median. Right? We may use the median, the central location somewhere here. Median. Right? Now, define the skewness. The skewness is the measure of asymmetry. What is asymmetry? Symmetric, asymmetric. Symmetric, asymmetric. Symmetric mean, right, both sides are, so when we divide a data set into two, for example this, right? So take a leaf, right? Leaf, this is almost sick, right? This is symmetric almost. And when we take a box like this, so we can take, if we divide by 2, so both sides are equal. This is symmetric. What is asymmetric? Asymmetric here, when we divide into 2, we can't get both sides are not equal. It's like this. right? So if it is a leaf, if you cut somewhere here, it is not symmetric. The shapes are different to each other. You know the butterfly, it is symmetric. Symmetric mean here right side and left side equal. Asymmetric, here the right side. Right side is heavier than the left side. Sometimes other way around as well. Also asymmetric. This asymmetric is called skewness. Skewed. Non-symmetric. Asymmetry means non-symmetric or skewed. So we apply this principle for data sets. Skewness refers specifically the non-symmetrical nature of frequency distribution. A given frequency distribution must be one of two states, perfectly mirrored symmetrical or distorted, skewed. Right? When you take the data set, it may be in two states. One, it may perfectly mirrored. Perfectly mirror mean those are symmetric. Symmetric mean left side, right side, right? Both of the side should be equal data set. And here asymmetric mean distorted data set is skewed. The ideal, the symmetrical distribution. You see, this is histogram, right? This is histogram originally, and we draw a line on the midpoint of these columns, and we connect all these midpoint of this histogram. So when we will receive, we will get smooth curve, smooth frequency curve, right? Smooth frequency curve. Now you see, right? You see both sides, both sides. When we see the both sides are equal, it's called symmetric. And you see, this is highest frequency. Highest frequency. Highest frequency is what? Equal to mod. And here the x value. This is the x value, no? X value. Look at here. Right side and the left side. There are equal number of equal values. Equal values and equal number of, not equal values actually. Say if it is 10, say if it's 12, this is 8. How many observation? Say 6 observation, also 6 observation. Why? The height are equal, and this height are also equal to this, and this height also equal to this observation, and this. So practical example, um, this principle always applies here. For example, when we take marks of students in a large number of students, large class, right? A large class. Say there are 1,000 students. There are 1,000 students, and when we take their marks, very few numbers, right? Only 2% of the students, only 20 or 10 students may get 95 marks. Right? 2%, top 2% of students may get 95 marks. But at the same time, opposite to this, uh, that to 9% of the students, right? Top 10% of the students, sorry, top 2% of the students, here 95, and here bottom 10% of the students may get 5 marks. Yeah, 95, 5. And it's very rare cases, right? Here also very rare case. And look at here, say another set of students, group of students may get 80 marks, and here 20 marks. And here you may see there are 60 marks, this number of students, and this number of students may get 40 marks. Yeah, this is 40 marks, and yeah, 60 marks. And in the middle, Many of them are getting 50 marks, right? 50. On average, here, say for 55 and 55, like this. So this is what? Symmetric. So here, mean, right? Mean marks at the middle, mean marks is equal to mod. And since the data is symmetric mean left side and right side, same number of observations, then we can see the median. So in the middle, right, this line has same mean, median, and mod. This x value, right? This x value, all these three measures are equal. So for symmetrical distribution, what are the key characteristics? The spread of values on either side is identical, right? So both sides, the data set, the spread mean the deviations, right? Mean deviation or mean deviation or quartile range or variance or standard deviation. Both sides identical mean same, right? Same. The spread of values on either side, left side or right side is identical. A vertical line divide the area into two equal parts. So this is the total area, right? This is total area. This line cut total area into two equal parts. This is right 50% of the area right side and 50% of the area in the left side. This is the vertical line actually. This is the vertical line. Skewness 0. So when the data behave like this, symmetrical data, then we can say skewness, the level of skewness 0. Right? The skewness is 0 because both sides are equal, symmetric. In this instance, mean equal median equal mod. How managers look at this behavior? The managers lens. This is predictable world. Average truly represent a typical experience. So this average. We can use this average to inference the dataset behavior. Look at this. This is skewed data. Earlier, we say when the data is symmetric, the skewed value is 0. Why? In the symmetric data, we have mean equal mod equal median. But here, we have three different values for mean, median, mod. And we have three different views. Here, this is the x value. Here, this is actually frequency distribution. This is frequency, this side. This is frequency now. This is x values. So, okay, behind the scene, there are a lot of histograms. And this is the top. This is the top and median, right? Like this. This is the histogram. When you look at here, this is x value mean, right? This is x value. This is a mod. Why? This is the highest column, highest bar. That is always represent mod. High frequency, mod. And the median, the mid value is here, right? Somewhere here. For example, we assume we give a data value for this. Say this is 50 and mean say 40. Sorry, yeah, 40, and it is somewhere 45, right? X value, the mean value is here. As our previous example here we discussed here. Look at here. What is the mod here? Mod is 20, 20. 2 times occurred. So mod is 20. But the mean is 35. and the median is somewhere here. Median is somewhere here, right? Look at here. This is mode, this is median, and this is mean. So this is what? Skewed data. Skewed data. The same principle applies here. You see, mode is here, right? Many times occurred mode, and median is very right far right 40, and median in the middle. So this kind of data set is called positive skewness. Positive skewness mean at mean value, the x value of the mean is higher than median, and median is larger than the mode. You see, this is x values now. The x values. Uh, Actually, I write it wrong way. It should be the x. This it should be 50. If it is 50, then it's 60, and this is 70. Right. So the mode value is 50, and the median 60, the mean 70. You look at here, mean is higher than the mode median, and median is higher than the mode. This is called what? Positive skewness. Visual identification. The tail of the right here. This is a tail, right? The tail. The tail. You can observe the tail in the right side. Here, right side mean the positive side is longer than tail in the left. You see the tail in the left side as well, but the tail is very short in the left side. Left side tail is short, and the tail in the right side is long. So this is what, when we draw this kind of data set, we can see like this. The shift, the higher outliers pull the mathematical average upwards. So here the mean value is high, right? Only one or two values, but those values are extreme, like the previous example 15, 20, 20, 30, 90. So because of this extreme value, the mean push up here, push up here. So how managers perceive this? Look at this thing scenario. Be careful using the mean here. A few high value outliers, like here 90 marks, like executive salaries, are inflating average, making it look higher than what is typical. So in this example, right, most of the students are getting below 30, but because of one student, it inflate the average marks, and finally we got 35. It's unacceptable because most of them are right out of 5, and 4 students are below 30. So because of the one extreme value 90 marks, it may give the mean become unreliable. Is skewed to the left. Same scenario. Here, this is the mode. This means highest number of frequency. The height represent, right? The height represent frequency. Frequency. This is x values, and here where say 60 and 50 is 40. Why? In the right side, it goes right side. It goes in the right side is the highest value, higher value. The left side is the lower value. And median 60, mode, right? So this is mode, right? Mode. This is median, and this is mean. This mean the mean is less value, right here 40, and mean is less than the median, that is 50, and the mode is less, the median is less than the mode 60. You see a tail. This is a tail. The tail, you can observe, the tail is longer than the right. Left tail is longer than the right. So where you can see the tail, left side, so that you can see that it's negative skewed, negative skewed. Visual identification, how we can look at this, see how we can see this kind of data in visuals. The tail on the left, so this is the left side, tail. Negative side is longer than the tail on the right. Shift the low outliers, track mathematical average down. Say, for example, we look at the age distribution of five group of people. Uh, One is 80, one is 70, one is 50, right? Another one got 10 years old. Another one here, say, uh, 60 years. So what is the average? Average 15, 20, 27. And how many? 5. Right? So the average marks somewhere, average age somewhere here. So due to this extreme value, it's bring down, right? It's bring down the average. So that's what the low outliers, low outlier drag the mathematical average down. Managers lens, how managers look at this kind of scenarios. The mean understate the typical value. The majority of the data is clustered at the right, right end, right? Most of the data set here. But due to the few low failures are pulling the average down. You see here, most of them are aged people, but only very young. So due to this observation, right, the average bring down. Mathematical average is not suitable here. So very careful on that. So we have discussed three type of data distribution. One is symmetric. So the symmetrical data set, we can see mean equal median equal mode. This is perfectly balanced. So this is typical. We can see 50% here and 50% of the data here. Mean, median are equal. A quick reference guide for identifying distribution shape. So by looking at this, right, you don't need to calculate mean, median, mode. If your histogram and smooth frequency curve look like this, so you can see the tail in the negative side, left side. So this is called what? Negatively skewed. So in this kind of data set, you can see mean is less than median and median is less than the mode. And the other way around, the positive skewness, you can observe the tail on the right. Actually, this kind of data has higher median, high mean than median, and median, high median than the mode. This is called tail points rates. So what are the insights you can get it? You don't always need to graph to know the shape. If you have the three metrics, what are the three metrics? Mean, median, mode. You can visualize the curve mentally, right? In your mind, you can draw this data by just having these three metrics: mean, median, mode. If mean is high, if mean is larger than the median or mode, it is positive. If the mean is less than the median or mode, that is what negative skewed. Right. So these are the visuals. No, these are the visuals, and how we can measure so the degree of the degree of skewness. Sometimes say uh, little skewed, sometimes extremely skewed, sometimes the medium skewed. So we can say like this: slightly skewed, slightly right, slightly negatively skewed, We can say like this. But how do we measure as statisticians? How do we measure it exactly? Right? That is the thing we are going to discuss. Quantifying, right? Quantifying the extent. How far, right? What's the degree of skewness? We know, we know what the shape look like, but how significant is asymmetry? So we know that by looking at the data, by looking at the mean and median and mode, we can say yes, this data is symmetric or asymmetric. If we are found symmetric, that is right, we can say that is skewness is zero. Skewness zero means there is no uh, the both sides of the data distributed equally. If it is right, sometime if the measure shows negative value, that is negatively skewed. Positive side, then positively skewed. So how we can get this kind of signs, plus or minus? This sign give us some idea whether the data is negatively skewed or positively skewed. Give some data. So we need to measure. To make comparison between different data set, we must calculate coefficient of skewness. You see, the coefficient of skewness. Simply we call them as SK. Skewness. Coefficient of skewness. The toolkit, there are three methods. Number one, Carl Pearson's. Carl Pearson's coefficient is most commonly used. Here they use mean and standard deviation. Bowley measures based on quartiles. So Q1, Q2, Q3, like that. And Kelly's coefficient based on percentile, right? P10 and P90. Based on that data values, he can suggest a formula. So there are three scholars give three different formulas to measure the skewness of the data set. If the skewness value is positive, we can say positively skewed, and if the skewness value coefficient is negative, it's negatively skewed. But the case is, even though if it is positive, you may compare two data sets, both of them are positive, but you don't want to know. You want to know what extent, which is more seriously skewed, which is slightly skewed. So that if we have the coefficient of skewness in exact term, we can apply values. The first one, the Carl-Pearson coefficient. This is the equation, first equation. Skewness. This is most common. Carl-Pearson coefficient. He used mean, mode, and standard deviation. Right? Using mode. If we in your data set you have no idea, no information about mode, but instead of that, okay, you have median. In that instances, you can use this formula, mean, median. Earlier we used mode, median, but if you use the median, you have to use 3. You have to multiply, you have to take 3 times of this difference, and should be divided by standard deviation, not these two. When used, I'll define this. The standard go to the metrics, general business statistics. Normally, the people uh, use either of this formula based on the availability of the data set. Second measure is Bowley's measure of skewness, coefficient of skewness. He used quartiles. You see the formula, skewness. This is extreme value, right? So they are dropped these two values here. This is lowest value, this is highest value. So they drop all these two, and they are working on the middle. This is upper quartile, lower quartile, and median. Right? First, they take Q3 and Q1, this value and this value, and minus 2 times Q2, right? And divide by interquartile deviation, quartile deviation, right? Quartile deviation, right? Interquartile deviation, right? Q3 extreme value, so you have to use the plus and 2 times median. Best used when extreme outliers might distort the mean or standard deviation, or when analyzing range data, so like income brackets like that. Uh, right, you may see some data set has extreme values. So in that instances, mean and standard deviation may not give a good idea about that data distribution. So then that instances we can use this kind of Bowley's measure of skewness, coefficient of skewness. And third Kelly's coefficient. He used, right, the percentile, right, the percentile. You know these, if it's a data set in the point that you may find Q2 or P50, and this is Q2, so Q1, this is Q3, this is 25%, P25 and P75. And you can see here P10 and P90. He drops only very few observations. Drop here and drop here. But in the quartile deviation, in the previous one, they took quartile, so they missed these observations in the previous one, and they missed these two times. So they consider only this distance. But this Kelly, right? He considers this. So the lossing this side and this side, very only 10% of the data loss. But here 50% of the data set loss. Why? The quartile, first quartile, lower quartile, and upper quartile. All these two missing, 30%, 50%. But here 90% of the data set, sorry, 80% of the data set they are considering. Here 10% loss, 10% loss. So 80% of the data set he considers. Based on the 10th and 90th percentile, 10th and 90th percentile, or decile, sometimes we call them decile, P10 equal D1 and P9 equal D9. Skewness, how calculate? P90 plus P10 and 2 times skewness is 2 times um, median, right? 2 times of median. And divided by the range means the highest percentile and lowest percentile. It's been D9 and D1 decile. Two extreme deciles. So when we can use this useful when you need to account for the broader distributions spread, specifically the extremes of the top and bottom 10%. Here we drop these very minor things. Now let's see, let us work with example data set. A monthly wage distribution is given, a mean 8,750 and median 9,200 and standard deviation 800. For this data set, which equation we can use? We can apply based on the data set. So they give mean, median, standard deviation. They not give mode. They not give information on Q1 or Q3, or they not give information on P10 or P90. So that Carl's Pearson's coefficient of skewness is appropriate based on this data set. The task, to calculate Carl's-Pearson coefficient of skewness to determine the distribution shape. So here is the data set. Mean, we know mean is 8,750, and the mod, so median 9,200, and we have to take 3 times 3, and standard deviation 800. So when we simplify this, we can get skewness equal minus 1.69, right? Minus 1.69 is negatively skewed because of the sign is negative. It is negatively skewed. And also we can mentally, without drawing this, here the mean is less than the median. So it's look like this. And this is mod, no, this is mod, and this is mean, and here median. So what? So it's negatively skewed. If it is positive, sign, then the distribution like this. So you can observe the mean in the right side. Interpreting the result. This is a wage distribution, no? Wage. So median here, mean here. Actually, it's not the mod. It should be a mod, but here so there are some precision mistake in the graph. The top always what mod. Sometime maybe equal to mean. Sometimes the wage distribution is negatively skewed. That is minus 1.69. It's negative. How managers perceive this? How managers as a management students, how you can perceive this? What the meaning of this? What are the insights? The average wage 8,750. This one is pulled down by tail of lower paid workers. So when we look at here, right? So there are many number of low salary people here, low salary employees, but people, few number of people, they are getting higher salary, right? Very few people, but they are getting higher salary, and it's bring, right? It's bring the mean on here. It's pulled down by tail paid workers. However, the median's 9,200 tell us that the typical workers actually earn more than the average. If you budget based on the mean, you say if you recruit based on the mean, you might undergo a typical salary. All right. Right. I think no. Here the frequency. This is a frequency, right? This is the top. This is a frequency. Frequency. When you look at this, there are high number of people. Higher number of people are they are getting higher salary, higher wage, right? Higher wage. But there are some few employees, right? Few employees they are getting low salary. That low salary pull back. They're extremely low. It means extremely low salary people are there. Few, right? Few extremely low salary people are there. That salary bring the average down. So earlier I misinterpreted. I'm sorry. The average wage 8,750 is pulled down by a tail of lower paid workers. Right, there are few, right? Few low paid workers. That low paid work employees bring it down. However, the median is 9,200. Tell us that typical workers actually, right? Typical workers, many workers actually earns more than the average. Right? Most of the employees are earn more than average. This is the average. If you budget based on the mean, you are safe. If you recruit based on the mean, right? When you recruit employees, you have to decide a salary. That instances, if you use the mean value to decide the salary, you might underquote the typical salary. It means you are you may there are a lot of chances to fix the lower salary to that. So be careful on that. Beyond average, skewness is beyond average. What are the takeaways? Look for asymmetry. Skewness reveals the lean of your data, and so that look at the asymmetry. So asymmetry, right? It's not right either right left or right side, maybe uh, higher than the opposite side. Check the tail. Positive lens right. Mean is higher than the median. So that's positive skew. You can see the tail on the right. Negative lens, it's left skewed, and mean is less than the median. And choose the right tool. So there are measures of skewness. Pearson, Bowley, Kelly, right? Based on the data available, given data set, we have to choose which one is more suitable. Choose the right tool. Use Pearson, Bowley, or Kelly's depending on whether you have standard deviation, quartile, or percentile. Or even when you use the Pearson, also you have to decide which formula based on the median or mode. Very careful. There are two formulas in the Pearson. In management, the average is rarely the whole story. The shape of the curve reveals the risk and opportunities hidden in the tail. Right. So that's all about this slide. And